Welcome back to The Explainer. Imagine walking into your kitchen while someone's cooking up a storm. Now look outside at an iron gate that's slowly rusting away. Or picture a lab where a scientist is heating up some chemical, or maybe electricity is zapping through water, breaking it down into these bubbling gases. At first glance, these activities look completely unrelated, right? But they're actually beautifully connected by one single underlying concept: chemical reactions. Today, we're going to break down the different types of chemical reactions and figure out exactly how they're happening all around us every single day.
So you might be wondering, why do we even bother classifying these millions of chemical reactions in the first place? Well, think about walking into a totally messy room where stuff is just thrown everywhere. If you tried to study millions of unique reactions without some sort of system, it would be absolute chaos. And this brilliantly illustrates the point. Imagine visiting this massive, sprawling library, but thousands of books are just chucked randomly onto the shelves. Finding what you need would be literally impossible, right? Books have to be categorized to make them easier to find. In that exact same way, scientists classify chemical reactions into specific groups, so they become way easier to study, predict, and ultimately actually understand.
Okay, let's dive into this. To organize our scientific library today, we'll be looking at four major categories: combination reactions, decomposition reactions, displacement reactions, and double displacement reactions. Let's kick things off with category number one: combination reactions, making one product. Imagine taking two entirely separate ingredients, mixing them together, and ending up with just one single unified product. Formally speaking, a combination reaction is a reaction where two or more substances combine to form a single product. The really crucial thing to notice here is that structural movement. We're taking two or more things and collapsing them down into exactly one thing. Now, what's really interesting about this is how beautifully simple the math looks when we actually write it out. Take a look at this classic equation where magnesium reacts with oxygen. If we break this down formulaically, you've got exactly two reactants sitting on the left side, magnesium and oxygen. They chemically combine to form just one single product on the right, which is magnesium oxide. It's the absolute perfect textbook example of a combination. Let's take a super quick detour because energy plays a massive role in all of this. When things combine, like calcium oxide reacting with water, for example, they often produce heat. Reactions that release heat are called exothermic reactions. Burning coal or even the respiration happening inside your body right now, those are great examples. On the flip side, we've got endothermic reactions. These actually absorb heat from their surroundings, which means they need a continuous supply of energy just to keep going. Moving right along to number two, decomposition reactions, breaking things down. For this one, I want you to imagine the exact opposite of what we just talked about. Instead of things coming together, picture one complex substance breaking apart. A decomposition reaction is a reaction where one compound breaks down into two or more simpler substances. And because chemical bonds are actively being broken apart here, these reactions generally require energy to happen. That makes them classic examples of those endothermic reactions we were just talking about. Here's a great visual anchor to help lock this concept in. Look at how two molecules of water break down into hydrogen and oxygen gases. You literally have one thing becoming two. Now, we just mentioned that these reactions need energy to force that breakdown to happen, right? Well, that required energy generally comes from one of three sources. We have heat, which gives us thermal decomposition. We have electricity, known as electrolytic decomposition. And we have light, which drives photolytic decomposition. Let's see how this builds into real-world applications. Thermal decomposition, using heat, is actually used to break down calcium carbonate when manufacturing cement. Electrolytic decomposition uses electricity to break down water into hydrogen and oxygen. And photolytic decomposition, that uses sunlight. A really beautiful example of this is silver chloride. If you put white silver chloride in sunlight, it gradually breaks down and turns completely gray. That very principle is exactly how traditional photography works. All right, on to number three, displacement reactions, swapping places. Think of this one like a sports analogy. Imagine a really strong star player entering a game and subbing out a weaker player. In the world of chemistry, stronger simply means more reactive. So a displacement reaction is a reaction in which a more reactive element displaces a less reactive element from its compound. It literally kicks the weaker one out and takes its place. Check out this classic equation.
Zinc plus copper sulfate yields zinc sulfate plus copper. Zinc is the more reactive element here. It's our star player. It steps right into the compound and kicks the copper straight out.
What's incredibly fascinating is how this actually looks in real life. As the zinc replaces the copper sulfate solution gradually loses its deep blue color, and solid copper metal is physically deposited right there in the container. You'll definitely want to remember this specific reaction and its visual changes. It comes up all the time in examinations because it just so perfectly demonstrates displacement.
Finally, we have number 4, double displacement reactions, exchanging partners. If regular displacement was like subbing a player out, imagine double displacement as two friends in a classroom simply exchanging their seats with each other. By definition, it's a reaction where two compounds exchange their ions and form two new compounds. The absolutely crucial detail to notice here is that both compounds are trading simultaneously. It is a clean, mutual swap. Here it is in action. Barium chloride reacting with sodium sulfate. Notice how the barium and the sodium perfectly swap partners. The barium goes with the sulfate and the sodium goes with the chloride, creating two entirely new chemical compounds.
So the really important point here is that these double displacement reactions often have a very noticeable physical result. Many of them, just like the equation we just looked at, produce what's called a precipitate. A precipitate is just an insoluble solid that forms during a chemical reaction. When barium sulfate forms, for instance, it shows up as this distinct white solid in the lab. Because of this, you'll often hear these referred to as precipitation reactions.
Let's pull everything together into a final comparison. This is essentially a cheat sheet for everything we've covered in this explainer. In combination, many reactants become one. In decomposition, one reactant becomes many. In displacement, a single reactive element swaps in. And in double displacement, two compounds cleanly exchange their ions. They all function fundamentally differently, but they are all distinct, amazing ways that matter transforms around us every single day.
Understanding these reactions really unlocks the mystery of the processes happening in industries, in our homes, and all throughout nature. So I want to leave you with a quick challenge. Can you identify a decomposition reaction that occurs in daily life or in industry? Think about cooking or manufacturing, or maybe even something happening out in the sun. Leave your answer and tell us your favorite reaction type down in the comments. Keep questioning, keep learning, and we'll see you on the next explainer.